pretty outrageous idea. In other words, all this real number stuff, all this partial differential equations, even all this set theory stuff, large cardinals, it's all fundamentally finite. This is my crazy head.
This is Professor Harvey Friedman's first podcast. At 18, he was given not only a PhD, which is outstanding, but the title of professor at Stanford University for his work in mathematical logic. The Guinness Book of World Records even listed him as the youngest professor ever. Curt Gödel, while alive, personally sponsored his last paper for the Proceedings of the National Academy of Sciences. And Professor Friedman founded the field of reverse mathematics. Gödel's incompleteness theorems are the most celebrated results in modern logic. The textbook examples are recondite, self-referential curiosities that no working mathematician tends to meet in practice. However, Friedman says they're pointing at the wrong target. The question is, can ordinary, finite math be trusted? His theorems suggest otherwise.
So now it's harder for the mathematical community to ignore foundations.
On this channel, I, Curt Jaimungal, interview researchers regarding their theories of reality with rigor and technical depth and probe at the foundations. Today, we discuss Tree 3, reverse mathematics, and the divine consistency proof, where
an angel is a weak form of God.
This is such a wide-ranging podcast, and I'm so excited for you to watch it. I hope you continue all the way until the end, especially as the professor and I bond. It was and is such an honor, and we close with why the professor thinks the foundations of math
are totally up in the air.
Professor, what misinterpretation of Gödel's incompleteness theorems bother you the most?
Well, one is that there really are two separate theorems, and they really are quite different, and most people aren't fully aware of the difference. So one is that in any sufficiently strong system, there are always statements that can't be proved or refuted. That's so-called Gödel's first incompleteness theorem. And the second one is that in any sufficiently strong system, the system cannot prove that it's without contradiction. It cannot prove that it's okay. And these are quite different things. I've heard some people interpret Gödel's theorem, first theorem at least, in the sense that we can't know things for sure. That's not quite what it says. It says there are always statements in any sufficiently strong system that can't be resolved within that system.
Okay, so what's then the difference between we can't know things for sure and then whatever Gödel's first incompleteness theorem actually says?
Well, Gödel's first incompleteness theorem, the most famous one, merely says that there are some things, given any particular logical framework, there's always going to be some things that system doesn't handle, that the system doesn't know whether it's true or false, meaning that the system does not prove or refute the statement. However, many statements will be provable and many statements will be refutable.
Okay, now this is a great opportunity for you to walk us through concrete incompleteness. So What's the punchline beyond what Gödel already showed?
All right, in a nutshell, Gödel showed that there were statements in the first incompleteness theorem, showed that there were statements that can't be proved or refuted in for example, the gold standard for foundations of math called ZFC. However, those statements are very far removed from what mathematicians actually like to think about. And that can be made more precise, but difficult to make completely precise, because what mathematicians like to think about is a little bit up in the air, of course, and changes over time. But basically, the original statements of Gödel are very far removed from the kind of mathematics that mathematicians very generally worry about and care about. So it's very different. What happened after the incompleteness, or the first incompleteness, what happened is that mathematicians wanted to know whether how far would this reach into the kind of mathematics that they care about. And there's been a long development of that. To give you a framework, the ZFC system was pretty much settled by 1930 as to what's in there. And by 1940, Gödel had already shown that a famous problem in set theory, a very famous fundamental problem in set theory, couldn't be refuted in ZFC. And then in the early 1960s, Paul Cohen showed that it couldn't be proved. So the two of them together showed that the continuum hypothesis, famous continuum hypothesis, is not provable or refutable with the ZFC axioms. However, the continuum hypothesis is generally regarded as extremely important in general set theory, but is regarded as extremely several steps removed in abstraction from what mathematicians normally do. And nowadays we can run searches and change normally into quantity. In other words, so many papers. I mean, I don't know that anybody's actually carried this out, but you can actually start putting some numbers on these things. So I think, will that help your understanding of what concrete incompleteness is? The idea is that the continuum hypothesis involves arbitrary sets of real numbers. Real numbers are fine in all through mathematics. And the combinatorial mathematicians probably want to go more concrete, but real numbers are fine. But if you talk about an arbitrary collection of real numbers with no patterns and no ways of generating it, just the notion of completely arbitrary set of real numbers, that's what the continuum hypothesis is about. And that's something that really is strikingly different than the normal kind of mathematics that mathematicians want to do.
Most ordinary mathematicians would just say that the continuum hypothesis is so far removed. It's almost like in physics, there are some counterexamples to what people ordinarily think of. So John Norton has this idea of a Norton's dome, where you can have indeterminacy in Newtonian physics, but then a counter to Norton, an ordinary physicist, let's just put that in quotations, would say that's highly contrived, that scenario, and also it's unphysical. And then Norton obviously has retorts like, yeah, sure, but tabletop physics with a like a rectangle or a square has the condition that my dome has. And then we can also say that black holes were thought of as unphysical before and a contrived solution. Einstein thought so. So what are the similarities and what are the differences here?
I think it has some similarities, but there's some differences. If you're talking about abstract set theory, which was a subject of great interest at one time, less so now, but there are still experts doing it. If you're going to do that, then the continuum hypothesis is not even remotely contrived. It's absolutely fundamental. We give it that. It's not contrived. However, the notion of arbitrary sets of real numbers, where the continuum hypothesis starts to gain traction, for arbitrary sets of real numbers, the most general kind of set of real numbers is not commonly understood. Well, I wouldn't say commonly, is not commonly appreciated as what mathematics is all about. In mathematics, one is generally concerned with the finite, of course, which is very concrete, the finite, and one is concerned with what might be called sequential processes, like real numbers. Real numbers are sequentially understood as an infinite series or infinite decimals. So decimal expansions. So the heart of mathematics somehow has a certain amount of geometric and combinatorial flavor to it that an arbitrary set of real numbers does not. And for more specific sets of real numbers that are more commonly dealt with in mathematics, like ones based on sequential limit processes, the continuum hypothesis is well known to be proved. It's not independent. It's proved. For instance, for so-called Borel sets of real numbers, the continuum hypothesis is a classic theorem that the continuum hypothesis holds there.
So let me ask you, Professor, why do you care about the continuum hypothesis so much? If many of your colleagues will say, look, yes, it's not contrived in the sense that you mentioned, but they don't care about it, why do you care about it?
Well, first of all, I don't particularly. I do care about the continuum hypothesis in a way, but that's not. I don't really care about it for concrete incompleteness, or so I call it tangible incompleteness now. In fact, it's totally irrelevant for tangible incompleteness. So I don't. Uh, I don't care about it for that purpose. Historically, it's very important. I actually got interested somewhat. I wrote an unpublished piece on why I believe the continuum hypothesis can be argued better to be false than true. And I'm not the only one who believes that. Many people, set theorists, believe that. I did get a little bit interested in it, but I think that's not really the topic at hand here, which is the tangible incompleteness. The Borel measurable sets of real numbers. My first big advance towards concrete incompleteness was finding statements in the Borel universe or the Borel sets of real numbers where you need more than ZFC or at least large hunks of ZFC. So my first ventures into concrete incompleteness passed through the Borel sets in the 1980s.
Where do you contrast with Hugh Woodin on the continuum hypothesis?
Well, Woodin is a card-carrying believer in abstract set theory and its intrinsic importance. He knows that mathematicians are not necessarily as enthusiastic about this area as he is, but he has a point of view that the continuum hypothesis is false. He wants to create a theory of how the entire universe of sets works. If you think the arbitrary sets of real numbers is abstract, away from the concrete, which it is, the entire set theoretic universe is incomparably more so. It's sets of sets of sets of sets of real numbers, for example, and much, much, much more than that. So he's part of the community that is really very much into abstract set theory. He has taken the view that the continuum hypothesis should have a definite answer, even if ZFC doesn't touch it, which ZFC does not touch it. It ought to have a definite answer. And the way that he and colleagues, associates, think about this is it's their job to uncover the truth. And although it is clear that the ZFC axioms have an intuitive, compelling appeal, are even visual and very much related to even finite intuitions in some sense, it is unclear at this point whether there's any kind of compelling, clear visuality to something higher than ZF that would settle the continuum hypothesis. I think he more or less thinks of exploring it as a scientist, saying what's more plausible than what, and what can we find compelling in some way, even if it's not compelling like ZFC axioms. Now, I've been dubious about this, and we went separate directions. We've known each other for a very long time. So he took this high abstract road, and I took the point of view that the future of foundations of math is how well it connects up with ordinary mathematical objects and ordinary mathematical intuitions, not extraordinary intuitions that only a few people have. So he and I are kind of the opposite directions.
When you're doing math, Professor, do you get the sense that you are also probing the truth?
Yes, but it's more philosophical. It's more foundational. I regard what the ultimate view of truth in mathematics is a totally open question that's been made more mysterious by my efforts. It's been made more mysterious, maybe not clarified, but made more mysterious. Because what I'm actually doing is I'm actually although Woodin and company have long since attacked ZFC because it doesn't have some of their abstract pets like measurable cardinals and other normally viewed as wild things. So they're comfortable with an attack on ZFC that it doesn't allow for the kind of very abstract objects that they believe exist. I attack it differently. I say it isn't even good enough to do finitary things that we care about. Now, when I say we care about, this is very much up in the air. I spent almost my entire life since 1967 trying to uncover uncontrived mathematical contexts in which the ZFC axioms are nowhere near enough. I started off with things that were grotesquely contrived, and spent 50 or 60 years trying to make them less contrived and connecting them up naturally with things that almost every mathematician can relate to immediately. That's been the program for 60 years. And that's a different kind of attack on ZFC.
Okay, let me attack this question in a different manner. So the way that people first learn about math when they're prior to university, maybe they learn the Pythagorean theorem, then they're told in university you're not supposed to have picture proofs. Okay, cool. Maybe they learn the quadratic formula, maybe they learn how to multiply matrices or what an integral derivatives are. And then they get to university, and if they take a math course or if they're specializing in math, you start to learn about axioms. And then from those axioms, you derive everything that comes upward. So maybe they have the idea in their head that math is about these seeds on the ground that grow trees, and the theorems are somehow the leaves on these trees. Is that the view that you have of math?
Basically, yes. In fact, it's been historically pretty much adhered to, that there's a purely logical part of math that has nothing to do, pure logic that has nothing to do particularly with mathematical objects. It could be anything. And that goes back to Aristotle with his syllogisms. And the big thing that Aristotle didn't have was the idea of binary relations between things. He had monadic things like being a man or being mortal, which is unary, so to speak, whereas less than between numbers is binary.
Mm-hmm.
There's a purely logical framework, and this it took to about 1900 for this to settle down completely as what's called the first order predicate calculus, or for short, predicate calculus. There's something called second order predicate calculus, but it's a confusion. First order predicate calculus, and that's the purely logical part of ZFC. And then when you apply pure logic, first order logic, you have proper axioms which you get to pick, and then you study what can be proved upwards from there. So there's the upwards from the purely logical axioms and logical rules of inference, which are fixed. Then you throw in proper axioms, and that's the framework that ZFC fits in. That goes up.
How do category theorists view math?
Category theorists have a different kind of point of view. Some of it is practical. That's the non-problematic part, the practical part.
Mm-hmm.
That it's good to think of categories because it facilitates a lot of mathematical work in topology and other places. The more extreme ones have a point of view that logic itself is a special case of category theory, that there's something more fundamental or more different than logic playing around with for all it exists and or. Well, that's just operations in category theory. Whereas the logician says, oh, no. Category theory is a special case of everything that we do, which is pure logic. And it happens to be a thing where we have objects called categories and we have operations on categories, just like ZF. There's nothing special about it. It's just another thing. So we both think we're more fundamental than each other. I will point out that Saunders MacLean, who I knew, he's a different generation than me, but he wrote a book called Categories for the Working Mathematician. In the beginning, he defines a category as a set together with blah, 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 blah. So he actually defines category theory in terms of set theory.
Yes.
So in a way, he wasn't one of the extremists.
Half of my day is spent in conversations and research. The other half is spent trying to remember what was said and read. That's where Plaud comes in, Plaud. I have far too many thoughts. I always tell myself that I'm going to remember them, and then I almost never do. It's incredibly frustrating. But I've been using Plaud for many months now, and it's a huge game changer. It's actually ridiculous. I've noticed that this channel's output theories of everything. If you've also noticed that it's increased in quality and clarity over the past few months, if it's improved at all, Plaud is responsible for a non-trivial chunk of that. I would say it's something like a 5% gain in thinking, and that workflow compounds fast. If you're a knowledge work, you know how valuable even incremental small 1%, 2% changes are. This trounces that. What I like is that it removes friction. I'll use the Note Pin S when I'm walking, moving around, or just thinking out loud. It's hands-free. I don't have to look at a screen, and I can stay present with the world. I don't have to worry that I'm going to drop my phone. Then I use Note Pro in more structured settings, when I actually want to capture and organize conversations more deliberately. So instead of ideas slipping away, everything gets captured, processed, and then turned back into something usable. It's basically a system for extending one's working memory into the real world. And if you know anything about intelligence, intelligence is highly correlated with working memory. So if your work depends on conversations, research, business, medicine, law, this kind of thing matters far more than you'd expect. They're also serious about privacy and security, SOC 2, HIPAA, and GDPR compliant. If you want to check it out, go to plaud.ai/CURT and use code Curt.
Okay, now how do these extreme category theorists, your words, not mine, I assume you mean topos theorists, how do they justify that logic comes from them and not the other way around?
Well, there's no question that they can do sensible mathematical work like this, which then they want to interpret it that way, whereas I don't interpret it that way. In other words, so the question is, the biggest rival to ZFC being the gold standard for foundations of math is some of these things the category theorists push. Topos theory, for example, as the real foundations. And I should point out, although they try to have a defense, that the big events in foundations of mathematics that most people hear about were not done by this point of view. It was done by our point of view. My point, I would say, I don't want to say my point of view, that's too extreme, but but the point of view that I like. I mean, the actual people, the actual results. After the fact, they did do some reworking, but never first. And in particular, concrete incompleteness. This is on our side. We don't have category theorists doing this or developing the techniques for it. So if you want to just put on blinders and look at what's happening in foundations of mathematics that can readily be described neutrally in some sense, because you can take my concrete incompleteness and say it's also not provable in the category systems either. It's equivalent, more or less. If you just put on blinders, you find out that the people and the events and the language of presentation for the big events has been all on, quote, my side.
How is the foundations of mathematics viewed by other mathematicians?
As pretty marginal.
Sorry, marginal as in unimportant or marginal as in...
right, unimportant and irrelevant is the most common reaction. However, there are these periods of history where some blockbuster comes to surface, Gödel especially.
Right.
And then some of the leading mathematicians in the world even suddenly take notice and make some comments about it. People start to say, well, I don't know anything about this, but maybe it is important, and now I'll go back to my own work. So you do have occasional things like that, but the feeling is that it doesn't really impact their work enough for them to take it too seriously.
That's similar in physics as well.
However, there's no doubt that what I am trying to do is to change that radically. How well I succeed is not quite clear. I've definitely made some inroads. See, there's a thing called, there are these weaker forms of incompleteness where you're not incomplete of all of ZFC, but you're incomplete of serious portions of it. And that's important. One famous serious portion of it is called Zermelo set theory, instead of Zermelo-Fraenkel. This is without Fraenkel's replacement axiom, so to speak. There's an axiom called replacement in the ZFC. Zermelo set theory is already an enormously strong system, far, far more than any mathematicians normally use. But I'll give you an example. There was a fairly well-known problem in what's called infinite game theory, and it's called Borel determinacy. This is the problem, and Donald Martin proved Borel determinacy using way more than ZFC, and that created some impression in certain parts of the mathematical community, no question, and but nobody had any confidence that this had anything to do with foundations. It was just overkill. It was just using something, probably overkill. Then I proved that there is no way to prove Borel determinacy without using infinitely many uncountable cardinals. In fact, uncountably many uncountable cardinals. That Zermelo set theory was not good enough to prove Borel determinacy. And that you needed at least a big hunk, an unusual hunk of ZFC to do it. And then Tony Martin looked at my argument and said, oh my gosh, this gives me a hint as to how I can prove Borel determinacy in ZFC. I would have never, he said, I never would have thought of using these strong methods that Friedman proved were needed. I never would have even thought along those lines. And now I see how to do this. So he published a famous paper, Proof of Borel Determinacy, using exactly the outer limit of what I said was needed, just beyond what I said it was not sufficient. So that's an interesting story. By the way, since then, I came up with a lot of statements that are not involving infinite game theory, another subject that has some interest but not huge. Just involving Borel measurable sets and this kind of descriptive set theory or analysis, which also requires uncountably many uncountable cardinals to prove. So there was an interaction. This is already 1980s and earlier.
So I'm laughing because I'm reminded of, I was watching a talk of yours and you were saying that there was some reporter who gave 3 titles to something of yours. One was that the man who blew up infinity or something like that. And the second was the man who wants to rescue infinity. And you said that one was discarded, but it was just some internal title. And then the one that you said was more accurate, maybe not still entirely accurate, but more accurate. Harvey Friedman is about to bring incompleteness and infinity out of quarantine. Right. That's a nice one. Okay, so I want to ask you about the foundations of math. That's the theme that unifies this entire podcast between us. So the foundations of math. Suppose someone was to make a similarly sensational title. They could say, Harvey Friedman says the foundations of math are what? Like, are wrong, are broken, are not known, are not investigated enough, are what? Like,
are
what
totally up in the air, or are more mysterious than ever.
Okay, interesting. Okay, but that would be a correct encapsulation?
That's my view, yeah.
Okay, so then obviously someone's like, so what? Like, wait.
Okay, so
Let me give you the analogy, because the analogy is, look, in physics, the people study the foundations of physics, and I'm terribly interested in that as well. But then the counter is, okay, yes, go, you few people, go about and study your foundations. I'm here building rockets. I'm here using quantum mechanics in the lab. Phones work, etc., etc. So I'm sure that's the sort of mentality that you see, that you encounter. So what, Harvey?
Yeah. All right. So I'm trying to deal with that directly, but it took me 60 years to get to the place I'm at. So important, new, attractive mathematical subjects appear, depending upon what size you're talking about, appear regularly. People get excited about there's some surprising result and stuff they're familiar with, and then they want to probe more deeply and get a complete analysis of it, whatever. There are two concepts among the many fundamental concepts in mathematics. Two of them are embedding and maximality. Both of them appear in undergraduate math and advanced math, uh, in many themes, in many situations. And what I do now is do what I call embedded maximality. I say that these two concepts can be combined into new striking theorems. And I call the subject embedded maximality.
Mm-hmm.
This is the title of the book that I'm trying to finish. This is novel in the sense that two very basic concepts, which are generally not mixed, are suddenly mixed with some surprise, not just mixed. The context in which I do this is not arbitrary sets of real numbers. The context is the rational numbers with the ordering less than. So, embedded maximality is the title of this book, and the context is among the most concrete situations in the whole of mathematics, which is simply the ordering of rational numbers without even addition or multiplication. And I show that there's a finite theory of this, where I look at all the finite embeddings that can be used for the maximality principle, and I analyze that first, and then I say, well, let's look at some very simple infinite maps, not just finite maps, but infinite maps within infinite domain.
Okay.
In the rationals, we're talking about, on an interval, it might be the identity on an interval is already infinite. All right. So, and then all of a sudden it completely explodes into beyond ZFC right there. So the plan is to define the subject very gently, called embedded maximality. Nice and friendly, simple definitions, half page to know what the subject is. State the finite theory, 30 or 40 pages of somewhat complicated stuff, completely analyzing the finite case. Attractive combinatorial mathematics of the kind that people have know and love. Nothing funny. And then say, well, I want to look at these finite maps on the rationals. I want to extend them by the identity map on the outer parts. In other words, if the finite function lives in here, let's extend it to be the identity above and below the function. That's a very simple kind of function, right? A very simple kind of infinite function. It's the identity almost everywhere, right? All of a sudden, you ask the same question: is this? Can you use these embeddings for the maximality principle? Can you use these embeddings? I solved it for the finite case completely, and the answer is it's independent of ZFC. That's the point of this book. So now it's harder for the mathematical community to ignore foundations. See, there's now this question of whether these theorems, there's a question of whether these theorems are in fact the outer extension usability theorem, OEU, the outer extension usability theorem.
Mhm.
Is this a legitimate theorem of mathematics or not? Has this been proved? Well, we have a proof using some monster cardinals that go way beyond ZFC, and we know ZFC is nowhere near strong enough to prove it. So is this math legitimate? Has it been proved? It's like the old classic issue about, is it okay to use functions that aren't given by expressions? You know, in the classical mathematics, everything, is a formula or something,
Yes.
The notion of arbitrary function came up relatively late, as you know, and people were concerned about it. Or even definition by cases originally, because you have a discontinuity that's artificially put on, right? So
I never heard of the definition by cases. What's that?
definition by cases. F of x is 0 if x is negative. F of
Okay.
x is 5 if x is positive.
Yeah. Okay.
Something like that.
Yeah.
You see, that doesn't come from the old idea of formula. All right. So anyways, if in fact the mathematical community falls in love with embedded maximality, because I figure out how to say it and motivate it, and connect it, by the way, with standard mathematics, which I have a chapter on that, how to connect it up with semi-algebraic functions and piecewise linear function, the stuff that the bread and butter. I do connect it up with that, though when that connection is for background, I don't get independence from ZFC, but that it's so tightly motivated and clear, and the finite part is so interesting, allegedly, then one is compelled to take seriously the outer extension embedding theorem, which has been only proved using much more than ZFC and cannot be proved in ZFC. So this subject, embedded maximality, is drenched with ZFC incomplete. How the mathematical community will view this is not clear. I have to roll it out.
And where are you with regard to that book?
Rewrote it 4 times or something. I rewrote it because it got such much more convincing.
But are you publishing slivers of it, or is it all going to come out at once?
I have there's a website that maintains maybe 30 or 40 one-hour lectures on it. So I have a complete record of that, and there's some manuscripts and unpublished stuff. Now, some of this is wrong. So I believe keeping the historical record is good for this. Some of these lectures, I overstated some stuff and I take it back and so forth. So it's not I don't have any problem with that. It's in fits and starts, but it's pretty. It's well on its way. In fact, I have to give a talk on it tomorrow on Zoom to a very small audience of experts. But it has to be done just right for something like this, because the skepticism that foundations is really important is so strong.
This video is sponsored by Shortform. If you want a free trial and an exclusive $50 off their annual plan, then go to the link in my description, shortform.com/TOE. If you're like me, you've encountered books that are so dense, finishing them is actually just the beginning. Shortform helps with that. Their book guides go far beyond pastiche summaries. They critique, they add context, they include interactive exercises, and connect ideas across authors. Take Gödel Bach or The Master and His Emissary, 2 of the most demanding reads in consciousness studies on the popular market. My method is I read the guide first, then the book, then I read the guide again. So it's a triptych of engagement that cements better understanding for me. The GEB guide maps recursive structures in a way that exhibits intellectual pleiotropy, where one insight branches into consciousness, computation, and self-reference simultaneously. Shortform covers philosophy, science, and psychology, ipso facto, the intellectual core of this channel. They publish new guides weekly, and subscribers vote on what books get covered next. Their browser extension, Shortform AI, summarizes articles and YouTube videos with a single click. Go to shortform.com/TOE for a free trial and an exclusive $50 off your annual subscription. That's shortform.com/TOE.
I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions moving forward. This sort of high quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, TOE is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off. Give a sense of how monstrously large the number tree 3 is.
Okay, well, I think the best way to talk about tree 3, there's some technical definitions that require some expertise in a subject called recursion theory. But one way I look at it is this. Tree of 3 is so big that you can't even prove it exists. That you can't prove it exists even in a strong system like piano arithmetic.
If that were true, that would indeed be mind-blowing, because any finite number can be shown to exist depending on your definition of exists.
I'm sorry. I misstated this. You can't prove it exists without using 2 to the 1 trillion pieces of paper. That doesn't mean that it's bigger than 2 to the trillion. It's incredibly bigger than that. I'm saying even with 2 trillion pieces of paper, that makes sense. You can't you're not even proving it exists.
Right.
I don't know how if that helps a lot, but and also a considerably stronger system than piano arithmetic. The statement I made is correct.
How does it compare to Graham's number?
Well, if I remember Graham's number, I think it's kind of not noticeable.
Yes. It's minuscule in comparison. Epsilon.
Now, you can play this artificial game in many ways, but this is a particularly elegant one that is mathematically very friendly. If you remember the definition.
Yeah, what is the definition of that number?
Yeah. Okay, you look at finite trees. Okay, first there's an infinite fact that's behind it. And then you think of this as a finite form, so to speak. And the infinite approximation is you have an infinite sequence it goes back to J.B. Kruskal. You have an infinite sequence of finite trees with 3 colors if you want. I do it with 3 colors. With 3 colors on the vertices. Each vertex has one of the 3 colors. You have an infinite sequence of finite trees. Then one of the trees is a part of a later tree, and part of means there's a color preserving embedding that's inf preserving. It's a slightly technical notion, but it's the obvious notion of homeomorphic embedding. There's a whole combinatorics that was well known of finite trees and how they fit together and what does it mean, but isomorphism and all that. Okay, so once again, and given any infinite sequence of 3 colored trees, finite, one of the trees in the list is embedded in one of the later ones in the list. This is a famous theorem of J.B. Kruskal. And I noticed, or maybe I wasn't the first to notice, but I made the first to do something with it. I noticed that this proof involved looking at all possible infinite sequences of trees, uncommonly many, and this proof was so far from being local. You might expect you just locally figure out this piece. It was so unusual, this J.B. Kruskal proof.
Yes.
And I proved why it was so crazy, so strange. I proved that Kruskal's theorem can't be proved in systems you'd expect it to be proved. Now, this is still nothing like ZFC. The ZFC incompleteness is something entirely different, a different level. But this is a micro incompleteness, so to speak. And I kind of proved that you need uncountable sets to prove this Kruskal thing. Okay? Now, how do you approximate the Kruskal thing? Because after all, it's about infinite sequences. Well, it turns out that from the things like the compactness theorem, well known in mathematics, you can show that if you put a bound, if you say that the ith tree has at most I vertices, the ith tree has at most I vertices. So you put a bound on the growth rate of this trees. Then you can find one of the trees is embedded in a later one, but you can even find a stopping place. You can even put a bound on how far you have to go up in order to know that. You follow me? In other words, you have to go a long way. So how far do you have to go up to get this? That's called tree of three. Tree of three says, how long do you have to go on like this so that one of them is embeddable in a later one? As long as the ith tree has the most I vertices and we have three colors. That's what tree of three is. How long do you have to go up there? Now, from general mathematics, you can prove from Kruskal's theorem, which is about the infinite sequences, you can prove that there is a bounding place. There is a place so high that you can get there. So if you know Kruskal's theorem, you actually know tree of three.
Okay, now what does this have to do with the relationship between infinity and the finite?
Well, this says that there's really a very close connection between the really big finite, the outrageous finite, and the small infinite. The smallest infinite is just omega, the size of the natural numbers. That's the smallest infinity. Cantor has higher infinities, like the real number line and all that.
Yes, I have a video about that.
Yeah. So the smallest infinity is very closely associated and approximated by the outrageously large finite. And we see this pattern over and over again. Now, I actually took this even more crazily, put on my crazy hat, okay? I said, suppose I'm a finitist. I'd say, okay, only finite things, maybe big things, maybe not even, I don't even like big things. If you're an applied computer scientist, you don't care about gigantic numbers. It's too impractical, right? Too impractical. You only care about things like a quadrillion or something is all about the most you could stand for. So what if I put my finitist hat on and I say, okay, all of mathematics I'm going to make finite. I know it's not finite directly, but I'm going to find finite approximations. And thesis, all of mathematical ideas are already represented in the finite. Pretty outrageous idea. In other words, all this real number stuff, all this partial differential equations, even all this set theory stuff, large cardinals, it's all fundamentally finite.
But
this is my crazy hat.
Yes.
A finitist hat. And in fact, the book, Embedded Maximality, has a section on purely finite forms, which shows, in a sense, that all these large cardinals beyond ZFC can be thought of in finite terms.
Now, let me ask you this.
Yeah.
What about ultra-finite terms?
Okay, you talking about ultra-finitism? Well, that's the point. That's the idea that you shouldn't go past very small numbers. That already 2 to the 100 is absurd.
Mm-hmm.
That's ultra-finitism. Yes, that's part of the crazy hat.
Interesting.
If you really want to push this really hard, all mathematical adventures can be properly imitated or realized in a computer screen. that level of detail. In other words, pixels with colors. Everything there is just pictures. That's already more than enough. Now, we kind of know that this is true in some sense because the human mind is thinking about things. I'm looking at this screen and I'm looking at everything. Everything I think about, my work, my pace, this is all well within the computer screen's size of information, which is only X bits, where X is, from the 1,000,
Sure.
whatever, right? So this is actually the most radical. And now the question is, all these fancy mathematical ideas we have, including large cardinals and ZFC, how do we actually say that we've actually properly represented them in a picture? I believe this can be done. And I think what's in my book is nowhere near that powerful, but it does suggest some things.
What are the large cardinals?
Yeah, so this is a whole subject in and of itself. The smallest large cardinal. Okay, from the point of view of a working mathematician, there's some cardinals that are tiny from the set theorist point of view that are already pretty damn large. Now, if you really want to talk about hard-nosed mathematicians, they usually live in the countable, but they are aware of the real line. So there's this cardinal called 2 to the aleph naught.
Yes.
So-called 2 to the aleph naught. So that's not really a large cardinal. Mathematicians aren't going to call that a large cardinal. If you're a real finite combinatorist, you might think of it as pretty large.
Of course, yes.
Okay. Then there's 2 to the aleph naught, and then there's 2 to the 2 to the 2 to the aleph naught. See, Cantor, I mean, this is maybe not exactly his original notation, but the idea is that given any cardinal, you can go to a higher cardinal. And so if you take the first omega cardinals, if you know what I mean, in other words, do it once, exponentiate it once, exponent it again, and exponent again, and so forth, you get a tower.
Sorry, Professor. Just a moment to interrupt, just briefly. For the layman, can they substitute infinity for the cardinal, for the word cardinal here? But if you take any
Yes, we're talking about different levels of infinity.
Great.
Yeah. Cardinal came up, Cantor defined these. Cardinal is an abstraction is the way we talk about levels of infinity. So I can talk about levels of infinity. The lowest level of infinity is the integers, represented by the integers. The next level of infinity that people know a lot about, is the real number line. However, there's something in between called omega 1, and there's a hierarchy: omega 0, omega 1, omega 2, omega 3. And the continuum hypothesis asks whether the real numbers are the second smallest infinity. Is the real set of real numbers the second largest infinity? And that's what's called the continuum hypothesis.
The divine consistency proof. Walk me through how God proves math is consistent. What does that mean?
Okay. There has been an idea that goes back to ancient theology, and Gödel took it quite seriously, and then I took it seriously because he did, that attributes or properties of things, being a human, whatever, properties are either good or bad, or either positive or negative, a classification of arbitrary attributes into positive and negative. This is very highbrow idea. Now, if you ask me practically, what does this mean, for real, actual attributes that people think about, who are not abstract philosophers and logicians, it gets a little bit strange. So we won't go quite there. We have this abstract idea that we're going to classify attributes as positive or negative. And there was this idea that God is the unique entity that's in the positive ones and none of the negative ones.
And in all of the positive ones, or just only?
Absolutely all. God is perfect. Now, Gödel took this in a different direction than I took it. he wanted to take this idea and actually proves that it's possibly necessary. So he has some sort of edge that there is a perfect being. He wanted to come up with some abstract philosophical principles that there's got to be something that has all and only the positive properties. And therefore he's proving in some sense that God exists, or he's proving that actually he states a weaker thing, that necessarily it's possible, or some what's called modological hedge.
Yes, please talk about your divine consistency.
This idea of classifying things into positive and negative intrigued me a lot. And there is something in mathematics that is very much like this. It's called an ultrafilter.
Yes.
It's a mathematical thing. Maybe you've heard of this. An ultrafilter on a set is you divide the subsets of the set into the big and the little. And everything is either big or little, and the intersection of two bigs is a big, and so forth. You can guess anything big has got to be infinite. Okay, or at least two elements. There's many ways to say this.
Sure.
And ultrafilters are a kind of useful things in a lot of different kind of mathematics. It was exploited by set theorists. If you have an ultrafilter that has a very strong property, namely, if you have a sequence of biggies, then its intersection is big. And that's not a finite sequence, that's an infinite sequence of biggies. Then the intersection is big. And that it turns out to be independent, whether there is such a thing. And that turns out to be a equivalent, more or less, to some large cardinal called measurable cardinals. So there is something bigger than ZFC there going on if you have a very strong kind of ultrafilter. So I started with this knowledge, right? Now, it turns out that we don't want to consider the ultrafilter. Okay, so there's an ultrafilter of all the big properties, of all the big ensembles, of all the positive and negative, remember. If you take all the positive ensembles, or the positive classes.
Yes.
That forms an ultrafilter. That's what Gödel started with. But if God is in there, it's all sucked up by God, right? So it's just the ultrafilter of all things that contain just this one special point called God. That's not very interesting. That's called a non-principal or trivial ultrafilter. Mathematically, that doesn't get you anywhere. Mathematically, though, you want to consider a situation where you don't have a lump like that. Like God is a lump right in there, right? You don't have a lump. Then I define what an angel is. An angel is a weak form of God. An angel is something which isn't in all the positives. That would be God. But it's in all the explicitly definable positives. In other words, it's a member of all the good properties, the positive sets that you can name, all the nameable ones. See, this is weaker.
Yes.
But that's a pretty good approximation of being a godlike, right? You're only in the good ones that are defined. All the other defined ones you're not in. And I call that an angel.
Yes.
This is just a theory in which you postulate that there is an angel, and you add the standard trappings you would like for a system, some mathematical infrastructure called the choice operator, and you get a system in which you can prove that ZFC is consistent. And the key axiom that drives it is the axiom that angel is, and there exists at least one angel. Now, this system could be worthless because it could be inconsistent, right? I could just be blowing smoke, right? But I can prove that this system is consistent using a measurable cardinal. And a measurable cardinal is something that the set theorists swear up and down is consistent, is okay, even though they can't prove it. So we've got ZFC proved consistent using angels. And we think that the angels are okay, that logically it's okay to have angels.
Now, speaking of putting on the crazy hat.
Yeah.
So what do your colleagues think when you tell them about this divine consistency, especially with the attributions of the monikers?
Okay, well, one of them said, Friedman, you're just trying to get grant money from the Templeton Foundation, which is known to be very friendly to theology. So that was one reaction. And this was actually from a very credible, known set theorist who should love it, actually, because, this is a set theory. I use all this set theory to do this, right? Some others are actually, they I think they think that that this is another reason to ignore me or something. But it's actually a pretty serious thing. It was refereed and accepted. It was actually, they found a referee that I don't know who he is. It was an obvious strong set theorist. He asked me why don't you go back and prove something better or something? No, I mean, he was being positive about it, but he liked it a lot. So I know that at least one obviously very skilled set theorist kind of bought it, kind of liked it. But they'll like it more. You see, there are all these concepts in theology. Omnipotence, God has all these properties. Omnipresence, omnipotence, unfathomable, whatever, all this stuff. And every one of those, I believe, has a serious set theoretic
analog. Interesting.
Or analog like this. I had the ambition to actually go through all of these properties of God and develop all of these connections with mathematics. But I have, my eyes are bigger than my stomach, So.
Yes. So then, did your math inform your theology, or your theology inform your math, or neither?
Well, this was a specific thing. I went to, speak of the devil, I went to the big famous Templeton meeting. There was a famous Templeton meeting, Congress. I was invited speaker, and there were other ones. Gary Kasparov, the world champion chess player, was there to talk about artificial chess players. Right, but it was basically a foundations of math meeting, and one of the speakers talked about Gödel's ontological argument and some, but I remember positive and negative properties, and I said, well, wait a minute now, this sounds like ultrafilters, and I think that there's something here of a different kind. So that's how I got into it. But I already knew I had a lot of them. I mean, the math was fully under my belt to do this. I just had to figure out what kind of math would really make this work, and how do I make the axioms. So I had to come up with the notion of angels to make this work.
So speaking of thinking of a theorem or a result and then going to the axioms, reverse mathematics.
Oh, yeah.
Tell me some of the biggest surprises.
That goes back to my real youth. I started to think along these lines in the late 60s. So I was fully familiar back then, soon after getting my degree, that mathematicians didn't really like foundations much. And they were suspicious of these things called formal systems that are bread and butter. And so I got interested in trying to show that these formal systems are really essentially purely mathematical in a sense, that there was some sort of mathematics in the axioms. That the formal systems were kind of forced by the mathematics that even these people, even these logic haters, like and do. So I then wanted to prove the axioms from the theorems. This is something that came out of being criticized by people who didn't like what I was doing. This was at Stanford. I had an office in math. I was a professor of philosophy. I had an office in math. So therefore, there was a teas at the regular teas in the math department. And so I used to go to these teas and try to convince them that logic and formal systems are important, right? So that's how that came about.
Tell me about how you think about math. What is your style of doing math?
Well, nothing is coming to mind immediately here. I can tell you what 95% of my mathematical my thinking is about. I got some contrived situation that I know is connected with. I got some contrived pseudo mathematical situation that I know is somehow connected to both math, although it's contrived and kind of ugly, and somehow I can squeeze out some heavy duty set theory out of it. Like what's going on in ZF. And if it knows too much about ZF, of course, then it's going to be independent of ZFC. See, that's the idea. Because if you can prove the consistency of ZFC, then you know you can't be in ZFC because ZFC doesn't prove its own consistency. I use that all the time. That's called Gödel's second incompleteness theorem, not the first, second. So I'm forever trying to make something mathematical that isn't. In other words, I'm trying to take things that are pseudo-mathematical and then redoing them and rethinking them to make them purely mathematical. So that's the kind of thing I'm doing all the time. There's always aha in there of the kind that you may be asking me about, but it's rather specialized. And I did this for 60 years.
Would you say that that's something that separates you from your colleagues or from the broader community? Is that a skill of yours that you seem to have that others don't?
Right. I am able to come up with attractive and perhaps unassailably attractive mathematical forms of things that are artificial.
Well, seemingly artificial, or at least they start that way, but because then you come back to concreteness.
Right. They start artificial, and then they're somehow reworked and connected with things that are not, so that they finally are solidly equivalent. I've done a lot of that. In fact, I do that all the time. I'm doing that in this book as we speak.
Yes.
Better and better. The book, it's got to a certain high level, but it's I'm pushing it as high as I could possibly tolerate, as high as possible for me. So I'm doing a lot of that kind of thing. And you asked the question, things like this have been done by others. It's not frequent. The most famous case of this is Leo Harrington. There's something called the Paris-Harrington theorem, which is a version of the finite Ramsey theorem, which is tweaked, and this time very successfully, to be independent of piano arithmetic. You can easily get an account of this on a search. Paris-Harrington. Jeffrey Paris did this, but it was comparatively clumsy. Harrington did this and turned it into gold. This is the kind of thing, he was able to do it. It was kind of interesting with Paris, no question about it. And Harrington gives him full credit for the initial step. But Harrington actually perfected it. So that's the 1970s. I'm sorry, I mean, I had the date exactly right. This is quite a while ago.
Sure.
And I did this. I did this around the same time. I did this at something that wasn't finitary. I did this with Cantor's diagonal theorem. I could tell you what I did with Cantor's diagonal theorem. This was the beginning of really getting into the concrete or tangible incompleteness. So Cantor proved that if I have an infinite sequence of real numbers, you can find a real number that's missing. Right? The real line is uncountable. So you're given an infinite sequence of real numbers, that you can find a real number that's missing. Now, in modern terms, you can ask, can you really find it? And it turns out that there is a way to find it. It's not continuous, though, but there is a way to find it that's Borelian. It's one of these sequential constructions. But there is a mapping from infinite sequences of real numbers to a real number that's off the sequence. This you could do. I mean, Cantor didn't think of this particular issue, but this is common in something called descriptive set theories. So there's a way of going from an infinite sequence of real numbers to a real number off the sequence. So I had this crazy idea. If you look at how this is done, the real number that you get depends on the order of the real numbers you're given. Not only does it depend on the real numbers you're given, of course, but it depends on the order in which you're given them. In other words, the decent way of doing this will give you a different answer according to which order the real numbers you're given is in. Like who's first, who's second, who's third, who's fourth, right? So I asked, can you do this independently of the order in which it's given? Can you do this by a Borel function, a sequentially defined function, a Borel function in such a way that it doesn't depend on the order in which the sequence is given? And I proved that you couldn't. This is impossible. It's called the Borel diagonalization theorem. It's actually the Borel anti-diagonalization theorem because it says you can't, right? And I proved this using uncountable sets. I proved this using some serious portion of ZFC that one normally doesn't use. So that's how I got it. It's an early event in this story.
What are your thoughts on constructive math and intuitionism?
On constructive math. I did write a number of papers in this area. Maybe I should start with my success in this area. I could state very easily.
Sure.
You know that there is one of the key successes of constructive mathematical thinking and constructive logic is the following property of the good constructive systems. If you can prove A or B, then either you could prove A or you could prove B. And this is considered to be a very strong success of the point of view, right? Because that's not true in the classical, meaning the non-constructive world. You can prove A or B in CFC or anything classical, but without being able to prove A or B. You may not be able to prove A or prove B. You can prove the continuum hypothesis or the negation of the continuum hypothesis, right? A or not B, right? But you can't prove either one of them, right? So, but on a constructive system, if you can prove one of the fundamental properties and the fundamental successes is that if you can prove A or B, you can prove A or prove B. There's another success that's stronger. If you can prove there's an integer n with a certain property, with a certain concrete property, certain effective property, then there's always a number n, so you can prove that works. If you can prove there is an n, then there's a particular n that you can that proves it. If there is an n such that if you can prove there is an n something, then there's an n such you can prove that works. That's even stronger. Okay, so I prove so that everybody's disjunction property is the first one, and the numerical existence property is the second one, right? So everybody's sort of writing papers. Well, he proved the disjunction property. Now we can also prove the numerical existence property by a similar argument or whatever. So I came in and I proved that for any reasonable system, if it has a disjunction property, it automatically has a numerical existence property. It's automatic. By a crazy proof I don't even understand today. A totally weird diagonalization argument that's crazy. Curt Gödel liked this. He published it. He sponsored it in the Proceedings of the National Academy of Sciences. So I have communicated by K. Gödel on this paper. The disjunction property applies to the numerical existence property. And I'm very proud to say this is the last paper he sponsored for the Proceedings of the National Academy. Other papers he sponsored, like Paul Cohen's Independence of the Continuum Hypothesis and Axiom of Choice. I mean, there's some real blockbusters that he sponsored. So I'm kind of honored that he actually put that in there. And then I visited him. He wanted me to come over. So I met the great man. That was an experience.
What advice do you have to a 20-year-old student?
Well, I think tangible incompleteness and embedded maximality is a real rich subject. Is one of the things in foundations they can really look at. I think that if they're philosophically inclined, at least, thinking about the serious foundational issues is going to be fruitful. But this is not so easy. And I think that with the embedded maximality stuff, I may have made it much easier, because here's a real live subject with an enormous number of open questions that's brand new. Now, I'm not saying that. I think they first should learn all the standard stuff, of course.
Yes, yes.
And of course, I want to tell you that I am biased about my own book.
Oh, of course, right. How is it that you go about attacking a new problem?
Well, I want to tell you, for quite a number of years, certainly very lately, my new problems are somewhat focused, surrounding this things like embedded maximality. So I can speak. I mean, I can speak more generally. Of course, you have to decide whether you want to invest more time on whether it's true or whether it's false. Let's say it's specific. Let's say you've got it down to a specific problem. Okay, so there's several different of things you could be talking about. You're talking about when the problem is actually fixed. When the problem is actually fixed, you really have to decide. Like I've played around with problems. I played around with the P equals NP problem a bit. You're familiar with that, of course. That's super famous. But I didn't really work on it hard. But you have to decide whether you believe P equals NP or not, right?
That's interesting. Okay, so you have to have a position on the problem?
Well, yeah, you don't necessarily have to take a position, but you have to take a position where your time apportionment is going to be.
Interesting.
Because if you pick the wrong side and you spend all your time on that, you could wind up with nothing. You still might wind up with something. We might refute a strong form of it, right, or something. You still could wind up with something. But it's good to develop some intuition for which side you believe more in and why. So that's one thing. Then you have to decide: is this really going to be something that needs a totally new theory? So what are the partial results going to be? I like a situation where you claw at it, getting very weak forms, and then try to build it up. These are lots of people's methods, not just mine.
What do you do when you're stuck on a problem then? Do you switch problems? Do you attack it continually? Do you start playing music? What do you do?
Well, I am something of a musician. I don't know if you knew this.
I know. I watched your YouTube channel. I do my research, Professor.
And I've got a lot better at that over the years. Better than anything you've seen, actually. And I also run a chess club. I'm not that strong a chess player. I didn't put the time in. I did play correspondence chess when it was okay, before the computers came in and ruined it. But I also started a book on the mathematics of chess. So I don't know if you want to go there, but
no, I just want to know about what is it that you do? What occupies your time? How much time do you spend on math? What does your desk look like? How are you productive? What part of the day?
Well, right. Okay. So I retired in 2012. I'm sorry. Getting old here. 2012, I retired. Yeah. And I'm single now. I have cleared off and made my life extremely simple in a kind of an apartment house which takes care of everything, including food. So I have an enormous amount of flex time. I don't write grant proposals anymore. I did some of that even after I was retired, but I rapidly quit that. But basically, I did get some money from Templeton Foundation. We should say that. But basically, I'm spending an enormous amount of time on math now. Maybe 12 hours a day. And music is going through my head all the time. That's why I don't have to practice too much and I can still play. So I do some of that. And I run this chess club for 10 hours a week, where I'm mainly coaching. There aren't strong players in the building, although sometimes they make me think.
Yes.
But on the chess side, I got very interested in the possibility of a very serious subject right at the border, right in the midpoint between math and chess. So I'm hoping to write a book on that, but I have to finish this book that I'm talking about. So I'm basically spending a lot of time, a lot of its exposition, perfecting the rollout of embedded maximality. And that involves lots of new concepts, lots of new math, refining concepts, running up into really hard problems I know I don't want to do now because the books will never finish. There's a lot of hard problems, and compiling them and putting the open problems in the book. So I'm really focused on this embedded maximality a lot. I also would like to write something serious about piano performance. How do professionals actually make it sound so smooth and emotional? What's going on there? This is very difficult to write about, but interesting. So I have a lot of plans. So I guess I'm just starting a serious part of my life now. Yeah.
What are your religious views?
Religion. Well, of course, there is the theology I told you about, but that's not meant to be what you're driving at. Yes, by positive and negative. Yeah, but I find that look, until we really understand how we came to be, i.e., origin of life, what is consciousness, all these things that make what I do look totally trivial. Everything's up in the air. Any conceptions of God make sense, make some sense. Until we understand a lot more, everything's on the table. That's the way I look at it. I also kind of I used to understand a little bit about what Einstein was saying about laws of the universe and some sort of non-standard notions of God that he had, although I don't remember exactly what he said. So I'm not part of any seriously organized religion, although I do maintain connections with a local rabbi that's quite important, actually. We're talking about some possible programs for gifted youth that we might do together. So that's about as far as I think I can go with this.
You were one of the youngest professors ever in America.
Yeah, I was assistant professor of philosophy at Stanford just before 19. I was actually 18. And I also had my PhD from MIT at that point. I wasn't a classic. I was a relatively strong mathematician, but I think I was more of a mathematical philosopher from the beginning.
Mm-hmm. Interesting.
Strong mathematically, but even stronger, I think, in some ways, given the age, the mathematical side of philosophy. I remember seeing a book that my mother left on the table and looking through it, and I think I was about, I don't know, 7 or maybe a little younger, 6. I remember looking through this book and telling her this book was totally worthless. And she looked at me and she said, "Why is this book worthless?" And I said, "Look, I looked up one word and I looked at the definitions the words in the definition, and then I looked those up, and then I went it came back in a circle. Nothing got explained. It was all in cycles." And I said, "That's worthless. That's no good. Doesn't make any sense. It's all circular." Now, this is, of course, very naive. And she says, "Well, I'm going to still keep the dictionary. I'm not throwing it away."
Right. So you brought me to where I was going to go next. And also to wrap up, speaking about a circle, I was going to bring up this story about when you were a child and you looked at the dictionary. I was going to connect that now to consciousness and to meaning. I wanted to know if after all these decades, have you come to some other realization about what words are, what grounds us, what are symbols, what does it all mean?
Well, that's more in the direction of what's normally called philosophical logic, not mathematical logic and not foundations of mathematics. There are really three different subjects that are really even the people involved are pretty separated. Philosophical logicians want to go deeper and look into what does and really mean. What does and or and not really mean? Now, foundations people do that a little bit with the distinction between constructive or intuitionistic and classical math, but they don't go as deep as some of the philosophers like to with this. I find this very fascinating, but I only have one life, and I think that I could, in fact, get very deep into this. So I don't know. I find it all mysterious. I'm not somebody who thinks, oh, well, this is uninteresting. I'm interested in too many things, maybe.
I see.
You know.
Then let me change the question. You said you only have one life. And at the same time earlier, you mentioned that you are attracted to some of the ideas of Einstein, who said that he's recapitulating Spinoza and that the universe is somehow God or what have you. Do you indeed believe you only have one life?
Oh, okay. That's very interesting. Well, there's certainly a way that's coming where we definitely have more than one life in a sense. And I had nothing to do with this, of course. And that's through AI. So if you leave a corpus of internet material like this interview, and you broaden your internet path, the AI knows about all this because it swallows the internet. At least right now it is, and it through probabilistic stuff that we all know a little bit about. I don't know a lot about it. Can extrapolate exactly what you would approximate what you would say in any context. I could be here after I'm physically dead, and you can have an interview with me, and the AI will answer based on their entire knowledge of my output. Now, this is maybe not the same thing you're thinking of, like the soul getting regenerated into another form of being in the standard sense, but it's an interesting thought. And this could be a very commonly purchased, I'm talking about in the future, commonly purchased device to have one's loved ones there for Thanksgiving or Christmas, carrying on conversations that are totally realistic. So that's a form of immortality, just through one's internet deposits, one's internet contributions. I'm sure that I'm nowhere near the first person to make this comment. In fact, I think, in a way, Pat Suppies was my mentor in a way at Stanford. Patrick Suppies. He's an amazing person. He died at the age of 92. Maybe 20 years ago or something. And he was a real polymath. He was a professor of 4 departments at Stanford. He hired me. He was the one who had this harebrained idea. He was chairman of the philosophy department at Stanford. He has a very large archive maintained by Stanford. You can just look at his collected works. And I remember the last video he made had hints of just exactly what I was saying. This is before the AI exploded. Absolutely. Before the AI exploded, he had said things just like this. It's kind of eerie. And his lecture speculating on this, I believe, is in that archive. If you just look at his very, very late lectures, because I think everything is there.
Professor, thank you for spending so much time with me.
Listen, I love this. I'm thrilled with this, and I think this is terrific. I enjoyed myself completely, and thank you for inviting me. At some points, they were very challenging indeed. So, I mean, you're a big shot in this. You've got this big podcast with these very well-known people spread all over the place. So it's new for me. If you think I'm good at it, maybe I should do more of it. I don't know.
I think you should do more. So just so you know about my interest, I'm interested in foundations in general. So foundations of physics, foundations of math, foundations of philosophy, but philosophy is almost always just about foundations anyhow.
At its best, by the way. Sometimes
Yes. And also even the foundations of biology.
Okay. I have said, and you could, I have said, I think you can find it. I don't know where I said it, but I said that I want to write it. My ultimate book is called The Foundational Life. And I do talk seriously. I mean, I've given talks in more formal settings where I'm asked, like I gave a talk, the Russian Academy of Science people, some of them who are logicians, asked me to give a presentation about my intellectual life. And they asked me some good questions, and I had to present a whole bunch of stuff about what I did. But I believe there is such a thing. In fact, I had this idea when I was, even before I got out of school, which is like 16 and 17, I had this idea of general foundations that I wanted to do foundations of math, foundations of physics, foundations of law, foundations of
Interesting.
of economics. I had a whole list of order of stuff I would do, and I would start with foundations of math because I thought that was the most well-developed one already, and so much to lever off of. And of course, what happened is I've had a failed life. I didn't get to the others much. Just a little bit. I got to the others. You know what I mean, in the sense that I had all this ambition to do these other ones. But I found the foundations of mathematics around when I was just before finishing school. I said, look, the key thing is to show that ZFC matters and that ZFC may not be sufficient for things that are really completely attractive mathematically, that are just totally mainstream, that are totally transparent, that are totally natural mathematically. And people thought this was too ambitious. Well, they were right in a way, but I may have succeeded. Well, we'll see how well I succeeded. But the point is that I always had this general foundations idea. I mean, even explicitly back when I was a kid. So when you said this, you and I are soulmates. You know that?
Yes. Well, let's continue to speak, sir, and I'm sure this won't be the last time.
Well, I hope not. I enjoyed this so much. You know, I didn't know that I could loosen up. I was worried about, accuracy and all this technical stuff, but you got me to loosen up.
You made it easy. Thank you, sir.
Okay. Thank you.
Hi there, Curt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at Jaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's CurtJaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted. There's zero spam. This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Curt, you've spoken to so many people in the field of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. CurtJaimungal.org or search Curt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/TOE, T-O-E, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. TOE is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/TOE, T-O-E. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that TOE listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use. I'm there with you. Thank you for listening.